Hello everyone, my name is Kartikey Pandey. I am a student of second year BTech in Computer Science and Engineering in Madan Mohan Malviya University of Technology, Gorakhpur. Today we are going to study about cache memory. Before starting to study about cache memory, let's know about the need of cache memory. So we'll start with the topic locality of reference in cache memory. It is also known as principle of locality. So let us first read the definition. Locality of reference is a term for the phenomenon in which the same values or related storage locations are frequently accessed depending on the memory access pattern. There is an alternate definition. Locality of reference is the tendency of a processor to access the set of memory locations repetitively over a short period of time. So, what does it mean? So, for example, while we are executing a program or we are performing a task, here we have a memory, and while performing the task, let our CPU, here is your CPU, is frequently accessing this address or this value. As you know, that the speed of CPU is quite faster than the speed of memory. So, to make it faster and more efficient, when the CPU needs to access a specific address or a specific value from the memory, we store that value in cache and then the CPU accesses the cache. We know that cache memory is significantly faster than memory. So the whole process becomes more efficient and thus our program needs lesser time to run. Now let's look at the types of locality of reference. So there are two types of locality of reference. First one is temporal locality and the second one is spatial locality. Now let's look at temporal locality. So the temporal locality says that if a program accesses one memory address, there is a chance that it will access the same address again. So, from this statement, we can understand that if our program accesses a specific memory address once, then there is a high chance that address will be accessed again by our program. This is known as temporal locality. So, it refers to reuse of specific data or resources within a short period of time. We can understand this as let this be a memory and this be a value. We need to access this value repeatedly. A very good example of temporal locality can be a loop, where while we run the loop, a single value is accessed repeatedly, and thus this value can be placed in cache to make this process faster. Now, let's look at spatial locality. It says that if a program accesses one memory address, there is a good chance that it will also access other nearby addresses. So, by this statement, spatial locality means that if our program is accessing a memory address, there is always a good chance that it will also access memory addresses nearby. So it refers to the use of data elements within a relatively close storage location. Nearly every program exhibits spatial locality because, as you know, that programs execute sequentially. So there is always a high chance that they will address sequential memory locations. And one of the very good examples is an array. As you know that arrays are contiguous memory locations. So if we are using an array in our program, then when we access one value of array, then we will obviously access other values of array, which will be contiguous memory locations. So for example, if this is our memory and we are accessing this value, then we will also access the next value. And that's what the spatial locality says. It says that if a program accesses a memory address, there is a good chance that it will also access other nearby addresses. Now let's move towards cache memory. So now we are going to study about cache memory. So as we have already discussed that cache memory lies between the CPU and the main memory, and it stores the value or the address which needs to be frequently visited by the CPU. Now let's see its features. Small size fast memory. So cache memory is a very small size fast memory. It is placed between main memory and CPU as we have already discussed. And it is a high speed volatile memory similar to RAM. It is volatile. That is, if the power is turned off, then all the contents in the cache memory are lost. It contains frequently accessed instructions and data. So cache memory contains most frequently accessed instructions and data, so that for accessing them the CPU doesn't have to go to main memory and can fetch them from cache memory directly, which saves us a lot of time. So it is located inside the CPU chip or on motherboard. So the cache memory which are located inside the CPU chip are also known as internal cache. These are L1 and L2, and those cache memory which are located on motherboard are called external cache, which are L3. So these L1, L2 and L3 are different level of cache memory. Like when CPU has to look for any instruction or any information, then it first goes to L1, that is level 1 of cache memory. It is the fastest of all three. So if it doesn't find any the required instruction or the required information, then it goes to L2. If it finds the information here, then it fetches it, and if it doesn't find, then it goes to L3. If it finds it here, then it fetches it and takes it to CPU. If it doesn't find, then it goes to main memory. Sorry. Then the CPU goes to first it goes to L3, and then it goes to main memory for that instruction. So in this way, CPU looks for instructions or data inside the memory. Now let's look at the working of cache memory. So as you have seen, the cache memory lies between CPU and the main memory. So the CPU first looks for the data in cache memory, and if it finds the data, then the data is transferred to the CPU from cache memory, and CPU executes it. If it doesn't find the data here in the cache memory, then it looks for it in the main memory. And if it finds it here, then it takes the data and makes the copy of the data in cache memory and then executes it, so that if in future it again needs to access that data, then it won't have to again go to main memory, which will obviously be slow, and it will be able to fetch the data from cache memory directly. Now another important thing is that the data from cache memory to CPU is transferred in form of words. We have already discussed about words in previous lectures. And the data, when it travels from main memory to cache memory, it travels in form of blocks. It is a major distinguishing thing between how the data travels between cache to CPU and main memory to cache. So now let's see here. Let's see the working in detail. The CPU initially looks in the cache for the data it needs. As I have already said, that CPU first looks into the cache for the data it needs. If the data is there, it will retrieve it and process it. So of course, if the data is found in cache, then the CPU will retrieve it from there and process it. But if the data is not there, then the CPU accesses system main memory. So if the data is not found in cache memory, then the CPU accesses the system main memory, that is this main memory, and then puts the copy of the new data in the cache. So when it finds that data in main memory, it puts the copy of the new data in cache and then process it. So before processing, the CPU puts the copy of the data that was not initially present in cache and was present in main memory, into the cache memory, and when that copy is put into the cache memory, then it processes the data, so that the next time if CPU needs to access the same data again, it will just retrieve the data from the cache instead of going through the whole loading process again. So as I've already said, that the CPU first copies the data which it was not able to find in cache memory and was able to find in main memory into the cache memory, and then processes it, so that if in future it needs that data again, it won't have to go to main memory again, and it would be able to fetch that data directly from cache. So now let's look at cache performance. So how do we measure cache performance? So a cache memory performance is measured in terms of hit ratios. So you must be thinking, what is hit ratio? So first we will have to know what is a hit. So if the required word is found in cache, it is known as cache hit. Like here we were discussing that if CPU finds the words in cache, it fetches it and processes it. So when we look for a word in cache and we find it, then it is known as cache hit. But the other case, if the required word is not found in cache, like when it was not found in cache and the CPU will have to look for it in main memory, then we will use cache miss. So if the required word is not found in cache, then it is known as cache miss. Now the hit ratio is defined as total number of hits upon hits plus total number of hits plus total number of miss, or it can also be written as total number of hits upon total number of CPU references. So what are CPU references? CPU references are when the CPU looks for the data in cache and when the CPU looks for the data in main memory. So if it is a hit, then it looks for the data in cache and finds it, and if it is a miss, then it looks for data in main memory and finds it. So essentially, this total number of CPU references is equal to total number of hits plus total number of miss. Similarly, we can define the miss ratio as total number of miss upon total number of hits plus total number of miss, or we can also define it as total number of miss divided by total number of CPU references, as we did in the case of hit ratio. Now there is another term known as cache access time. So how do we define cache access time? It is also known as cache hit time. So the time required to access word from cache is known as cache access time. So the cache access time is simply defined as the time required for a word to be fetched from cache. Now, what is miss penalty? Miss penalty, this term is also known as cache miss penalty. Cache miss time penalty. So it is the time required to fetch the required block from the main memory. Pay attention. Here we were discussing about word and here we are discussing about block. Why? Because we have already told that when the data moves from cache to CPU, it moves in form of words. But when the data moves from main memory to cache, it moves in the form of blocks. So time required to access word from cache, that is time required by the CPU to access the word from cache, is known as cache access time. And this cache miss time penalty is the time required for the CPU to fetch the required block from the main memory. Now let's discuss about the average access time of CPU. So, as we have seen that CPU either finds the data inside the cache and fetches it in form of words, or the data is not present in cache and then it has to look for the data in the main memory, and when it finds it, that it makes the copy of the data in cache and then fetches it and processes it. So, this average access time is the time taken by the CPU to access the data in whole of this process. It can be calculated by the following formula, that is hit ratio into cache access time plus 1 minus hit ratio into miss penalty. So this hit ratio, as we have already discussed, is simply total number of hits upon total number of hits plus total number of miss. This cache access time is the time required by the CPU to access the word from cache, and this 1 minus hit ratio will simply be a miss ratio, because you should have figured out that hit ratio plus miss ratio will always be equal to 1, and this miss penalty is simply cache access time plus time required to access main memory. So we can represent it as hit ratio is represented by small h, cache access time is represented by TC. This 1 minus hit ratio is of obviously 1 minus h, and this miss penalty is represented by Tm. Now let's understand this average access time of CPU in a better way by solving the following question. So let's see what the question says. The access time of a cache memory is 100 nanosecond and that of main memory is 1000 nanosecond. It is estimated that 80% of the memory requests are for read and the remaining 20% for write. The hit ratio for read access only is 0.9. A write-through procedure is used. So first of all, what is a write-through procedure? So a write-through procedure is a procedure. First of all, there are two procedures for writing a memory: write through and write back. So in write through procedure, the cache and storage memory, a cache and main memory are updated simultaneously. In the write through procedure, the cache and main memory are updated simultaneously, while in write back procedure, the cache is updated first and the main memory is updated later. So here we are using write through procedure. Now let's see what it is asking. So what is the average access time of the system considering only main memory read cycles? So we have to find the average access time of the system by only considering memory read cycles, not write cycles. Now, what is the average access time of the system for both read and write cycle? Then again we have to calculate the average access time of the system for both read and write cycle. And what is the hit ratio taking into consideration the write cycles? And we also have to calculate what is the hit ratio taking into consideration the write cycle. Now let's solve the question. So as we already know that average access time of CPU is equal to H, that is hit ratio, into TC, that is cache access time, plus 1 minus hit ratio into TM, that is cache time penalty. So now to calculate this, in this case here, as we can see, the hit ratio is 0.9 and the access time for main memory is 1000 nanosecond and the access time for cache memory is 100 nanosecond. So we can calculate it as the hit ratio is 0.9, the cache access time is 100 nanosecond, it will be 1 minus 0.9 into, of course it will be cache access time plus the time to access memory, which is 100 plus 1000. Now let's calculate it. So it will be 90 plus 0.1 into 1100. It will be 90 plus 110, which is 200 nanosecond. So the average access time of CPU has been calculated by us as 200 nanosecond. Now, what was the second question? What is the average access time of the system for both read and write cycle? So let us first calculate. Of course, it is for a read cycle only. We have not taken into consideration the write cycle. Now let's see how we will be able to calculate the average access time for both read and write cycles. So let us first calculate it for write cycles only. So average access time for a write cycle, as it is mentioned in the question that it is a write through procedure, so the both cache and main memory are updated simultaneously. So we will just take 1 into max of the cache access time and main memory access time. It will give us the access time for write cycle, which will be 1000 nanosecond. Now let's move forward our next question, that is what is the average access time for both read and write cycle. So average access time for both read and write is equal to, so of course there are 80% of read requests and 20% of write requests. So it would be 80 by 100 into, of course, the average access time of read request, that is 200 nanosecond, plus 20 by 100 into the average access time of write request, that is 1000 nanosecond, which will give us 160 and 200, which is 360 nanosecond. So we have found another answer, that is the average access time for both read and write, that is, and it is 360 nanosecond. Now we have to calculate what is the hit ratio taking into consideration the write cycles. So we were given the hit ratio for read cycles only. We have to calculate hit ratio for both read and write cycle. So here, as we have already seen that 80% of read requests and 20% of write requests are there, so we can simply write 0.8 into 0.9, that is hit ratio for read access, plus 0.2 into 0. Why I have written it 0? Because hit ratio for write request is always 0, as of course you can't find a write request in cache, you will have to write it in main memory. So here, after calculation, we will get 0.72. So this is the hit ratio by taking into consideration both read and write requests. So now we have all the answers, that is average access time of CPU, which was 200 nanosecond, average access time for CPU when both read and write requests are considered, it was 360 nanosecond, and the hit ratio when both read and write requests are considered, it was 0.72. Now let's move towards the next topic, that is levels of cache memory. So In cache memory, as we have already discussed, there are three levels. Let us discuss each level one by one. So the first level is level 1 cache. So it is the fastest cache and usually comes within the processor. So the level 1 cache is the fastest of the three, and it usually comes within the processor. That is, it is usually built inside the processor. Typically, it ranges in size from 8 KB to 64 KB and uses the high-speed SRAM, static RAM. We already discussed about static RAM and dynamic RAM in the previous video. Instead of the slower dynamic RAM used for main memory, as we had discussed before, that the static RAM stores the data as long as the power is on, but the dynamic RAM stores the data for a very short amount of time. So that's why static RAM is faster than dynamic RAM. And of course, but dynamic RAM is cheaper because it consumes less power. So, but let's focus on the current topic, which is the range of the L1 cache is from 8 KB to 64 KB, which is quite small, but it is very high in speed. That is, it is very fast because it contains SRAM and it doesn't use a slower DRAM, which is used in main memory. And of course, as it lies inside the CPU or inside the processor, it is referred to as internal cache or primary cache. Now let's move towards next level, that is L2 cache. So it is, of course, it is larger in size but slower in speed than L1 cache. So the L2 cache is larger in size but slower in speed than L1 cache. We have already seen that as we increase the size, the speeds become slower because we have to balance the cost. Now it stores recently accessed information. So the L2 cache stores the recently accessed information. It is also known as secondary cache. The L1 cache was known as primary cache and it is known as secondary cache. It is designed to reduce the time needed to access data in cases where data has already been accessed previously. So, as we had discussed that the CPU looks for data in cache, and when it doesn't find it there, it looks for it inside the main memory and then copies the data into the cache so that the next time it can access it directly from the cache. So the L2 cache helps us in those cases. As it is written here, it is designed to reduce the time needed to access data in cases where data has already been accessed previously. So here it is given that where the L2 cache lies. So the L2 cache comes between L1 and RAM and is bigger than primary cache, as we have already discussed that it is larger in size. The size ranges from 64 KB to 4 MB, and as we can see here, here comes CPU, then it is directly connected with L1 cache, and then it is connected with L2 cache. The L1 cache is connected with L2 cache, and the L2 cache is connected with RAM. That is, L2 lies between L1 and RAM. Now let's discuss about the next level of cache, that is L3 cache. So the L3 cache memory is an enhanced form of memory present on the motherboard of the computer. So as L1 and L2 were lying inside the CPU, but L3 cache lies on the motherboard. L3 cache is a memory cache that is built into the motherboard. It is similar to the first point. It is used to feed L2 cache and is typically faster than system's memory, but of course slower than the L2 cache. So the L3 cache is used to feed information to the L2 cache and is typically faster than the system's main memory. So it is faster than the system's main memory, but of course it is slower than L2 cache, which is slower than the L1 cache. It has more than 3 MB of storage in it, so it has more storage than L2 cache because of course it is slower, then it will have more storage. And not all processors have this L3 cache, so it is not necessary that all processors have this L3 cache. Many modern processors are coming with L3 cache because it is used to enhance the performance of L1 and L2 cache. So L3 cache is simply used to enhance the performance of L1 and L2 cache by coming between the main memory and L2 cache. So now we will move towards our next topic, that is cache mapping. So what is cache mapping? So cache mapping is a technique by which content of main memory is brought into the cache memory. As we have been discussing so far, that when CPU search for some data, it first searches into the cache memory, and if it finds it there, then it fetches it from there and executes it. Otherwise, it looks for it in the main memory and then makes a copy of it in the cache memory so that it can access it through cache memory in future. So cache mapping tells us the technique by which that content which was not in cache and was in main memory is brought into the cache memory. So it is transportation of data from main memory to cache memory. As you can see here, here is our main memory, here's our CPU, and here's our cache. So how the data from main memory is mapped to the cache memory and from where CPU accesses it. These are the things that we discuss in cache mapping. There are three types of cache mapping: associative mapping, direct mapping, and set associative mapping. Now we will be discussing about each type one by one. Let's start with direct mapping. In direct mapping, each block of main memory can be placed in only one specific cache line. The mapping is defined using a simple formula, that is, cache line is equal to main memory block number mod number of cache line. So every block has exactly one location in cache. Now, let's look at an example and understand how our physical address looks and what each part specifies. So, our physical address is divided in three parts: tag bit, cache line, and block offset. The tag bit and cache line together determine block number, and the block offset determine the specific word. Now, as we have as you can see here, in this example, we have assumed that block size equal to 4 words. To determine the number of blocks in main memory, we can simply use total size of main memory, that is 32 words, divided by block size, that is 4 words. So we will have 8, that is, we will have total 8 blocks in the main memory. Similarly, we can determine the number of cache line by dividing the total size of cache memory, that is 8, by the total size of cache memory, that is 8 words, divided by block size, that is 4 words, which will be equal to 2. So we will have 2 cache lines. So now we will have to determine how many bits do we have in physical address. So since we have 32 words, that is 32 is equal to 2 to the power 5. So we will need 5 bits in our physical address. So we will have total 5 bits. Now, to know this block offset, since this block offset represents words and each block has 4 words, so and to represent 4 words, we can calculate how much bits we need. So 4 is equal to 2 to the power 2. So we will need 2 bits. So block offsets will be of 2 bit. Now we have this cache line and tag bit. So as you can see, there are only two cache lines. So and we can represent two cache lines using only one bit. So the cache line will be of one bit only. And since this total physical address is of 5 bits and 2 bits is of block offset and 1 bit is of cache line, so the tag bit will need 2 bits. So now we have calculated how our physical address will be divided in tag bit, cache line and block offset. Now let's see what are the advantages and disadvantages of direct mapping. Let us first look at a major disadvantage, that is, since direct mapping maps each block of main memory with exactly one block of cache memory, sorry, with exactly one cache line of cache memory. So there arises a condition known as conflict miss. For example, here we can see that this block 0 will be stored in cache line 0 because we have the formula here, that is cache line is equal to block number, that is 0, mod total number of cache lines, that is 2. So it will give us 0. So the block number 0, block number 2, block number 4, block number 6, all these block numbers have to be mapped to block 0, but at a time the have to be mapped to cache line 0, but at a time cache line 0 can contain only one block. So for example, if block 0 is in cache line, that is cache line has W0, W1, W2 and W3, and then CPU requests for block 4 which was not in cache and was in main memory. Then this block 4 needs to be moved to cache. But to move block 4 in the cache memory, we will have to empty the block 0 despite of having an empty cache line, that is cache line 1, due to the rigid formula used in direct mapping. Thus, this generates a major disadvantage which we have to face while using direct mapping for mapping main memory to the cache memory. And let's look at the advantages. So some advantages are as follows. First advantage is, since direct mapping is very simple and works on a simple formula, therefore it needs very simple hardware. We don't need a complex hardware for achieving the direct mapping. Another advantage is that it provides us fast access. Since every block in main memory is mapped to exactly one block in cache memory, so it gives us a very fast access to the main memory. And of course, because of having simple hardware, it is of low cost. And of course, as we have discussed, the disadvantages are high conflict misses because each each memory block is strictly mapped to single cache line. Therefore, it leads to many conflict misses, as we have already discussed above. That even if we have empty cache lines, then also we'll have to replace data from one cache line to store data from main memory because we have a rigid formula. And this also leads to poor cache utilization because even when we have empty cache lines, that is empty storage in cache memory, still we have to replace the data which has already been stored in cache memory to store another new data. So the direct mapping also leads to poor cache utilization. Now let's move towards associative mapping. Now let's look at the associative mapping. So it is the fastest and most flexible cache organization, and it uses associative memory as name suggests associative mapping. In associative mapping, caches are made up of associative memory, as we have already said. And associative memory is used to store both the address and content of the memory word. So, associative memory is used to store both the address and content. Now, it permits only location in cache. It permits any location in cache to store any word from main memory. That is, it enables any word from main memory at any place in the cache memory, which does not happen in other mappings. As we had discussed in direct mapping, that each block in cache memory could have only one location in main memory. Each block in main memory could have only one location in cache memory. But here in an associative memory, any block can have any place in cache memory. Let's see this with an example. So let's suppose that we have main memory of 32 words size and a cache memory of 8 word size, and block size is equal to 4. That is, one block can contain 4 words. So of course, for number of blocks, we have already did it in direct mapping, is equal to 8. We will have 8 blocks in main memory, and number of cache lines is equal to 8 divided by 4, that is 2. 2 cache lines in cache memory. Now, in case of associative memory, the physical address looks like this. It is divided in two parts: block offset and tag bit. Here, as was the case in direct memory, block offset specifies the word, and this tag specifies block number. Notice that we don't have a cache line bit here because cache line is not fixed for every block. So now let's look at this example. So let's assume that right now in our cache memory we have address 010 this is tag bit and 100. So here the tag bit is 010, which means it is representing the second block. And here in the second block we have word 8, word 9, word 10 and word 11. And here the tag bit is 100, which represents the fourth block. And in this fourth block we have word 16, word 17, word 18 and word 19. So now we will see how we will determine if it is a cache hit or cache miss. Let's the CPU looks for a physical address 01011. So we will divide this in two parts. Now you must be wondering how I decided that how many bits does tag have and how many bits block offset has. So we can calculate this simply as we have 32 words. So the total size of physical address can be determined by this 5 bits. So the total size will be 5 bits and the block offset determines the word and each block has 4 words. 4 is equal to 2 to the power 2, so it can be represented by 2 bits, so it will be of 2 bit. Now the remaining bits will belong to tag bits. So here again let's come to the example. So it was looking for the CPU is looking for the address, physical address 01011. We divide in two parts. We divide it in two parts. This part is tag bit and this part is block offset. So now we will have to look for this tag bit one by one in each cache line. Yes, in associative mapping, there is no fixed location for blocks. So when CPU searches for data, the tag is compared with all cache tags simultaneously. That's why it requires content addressable memory. So let's come back to the example. So here we will look for this tag bit in our cache memory and we will find it here. So it will be a hit because we have found this tag bit inside our cache memory. And of course from here we can specify which word the CPU was looking for, and it is 11, which means it was looking for third word. This is zeroth word, this is first word, this is second word, and this is third word. So it was looking for word 11. Now let's see another example. Let's say that CPU is looking for a physical address 10100. Now again we will divide it in two parts, block offset and tag bit. Now again the CPU will look for this tag bit in our cache memory, and this time as you can see this tag bit, that is 101, is not present in the cache memory. So this will be a miss. It won't be a hit. So you must have understood that in associative mapping, how does CPU determine that if it is a cache hit or it is a cache miss. Now let's look at the advantages. So here are some major advantages of associative mapping. The first advantage is it is very flexible. Of course, it is flexible as compared to direct mapping. In direct mapping, we were allowed to map each block to a specific cache line only, but here we can map any block to any cache line, and thus it also has lower conflict misses, which were quite high in case of direct mapping. And due to these properties, it also leads to better utilization of cache, because here if cache memory if some cache line is empty, then it can be easily used to store the incoming block memory, the incoming data, which was not the case in direct mapping. Now let's look at some disadvantages. Yes, associated mapping also has some disadvantages. So as we have seen that it is quite flexible and it leads to lower conflict misses, it has better cache utilization. But you must have noticed that the cache memory also stores the address, and the CPU looks for the tag which specifies the block number each time it looks for the data in the cache memory. And for these things to happen, we need complex hardware, which is expensive, and thus associative mapping becomes expensive, and it also needs parallel comparison of all tags. So although associative mapping gives us many advantages by being very flexible, allowing us to map any block to any cache line and giving us a better utilization of cache memory, it also has disadvantages that are it needs complex hardware which makes it expensive, and it needs parallel comparison of all tags. Now let's discuss about set associative mapping. Let's discuss set associative mapping. So, in set associative mapping, we will be seeing that it is a combination of direct mapping and associative mapping. In set associative mapping, caches divide into sets, and each set contains multiple lines. A memory block maps to one specific set, as if you can remember, in direct mapping, one memory block used to be mapped to one specific cache line. But here, a memory block maps to one specific set, not a cache line, but can be placed in any line within that set. And similar to the associative mapping, where any memory block can be placed in any cache line. Here, memory block maps to one specific set but can be placed in any line within that set. We will understand set associative mapping by taking an example. Here, in this example, we will be talking about two-way set association, and we will see two-way set associative cache. So here it is an example of two-way set associative mapping. Now, first of all, let me tell you that why it is called two-way set associative mapping. Here we have our cache memory, which is of size 16 words, and we have our main memory, which is of size 64 words. He, sorry, here block size is 4 words. So number of blocks in main memory is simply equal to 64 by 4, which is 16, and number of cache line is equal to 16 divided by 4, which is of course block size, that is 4. So here we will be dividing our our cache memory in two parts. Here you can see that in both the parts there are in each part there are two cache lines. Let us name this set 0 and this set 1. So first of all, you shouldn't be confused that since we are dividing cache memory in two parts, therefore it is called two-way set associative mapping. No. Here the two-way set associative mapping is called two-way set associative mapping because each set contains two cache lines. So this number comes from how many lines are there in each set. Here in each set we have two cache lines. Therefore it is called two-way set associative mapping. So let's move further and see how do we decide that which block goes to which set. So as we used to decide in direct mapping, this also has a similar formula which you can see here. To decide that which the block number will go in which set number, we have the formula that is set number is equal to block number mod total number of sets. So for example, if we have to calculate that where this block 0 will go, then we will calculate 0 mod total number of sets. Here we have two sets is equal to 0. Therefore this block 0th block will go in set 0. Similarly this first block will go in set 1. Second block will go in set 0. Third block will go in set 1. Similarly, we can calculate this for each block. Now let's look at how the physical address looks. So here the physical address is divided in three parts as it used to be in direct mapping, but here the middle part is not called cache line bit, it is called set number. So first of all we will have to calculate that what is the total size of this physical address, which can be simply calculated by knowing that the main memory contains memory size is 64 words. So 64 is equal to 2 to the power 6. So we will need 6 bits in our physical address. Now here block offset represents words, similar to direct mapping and associative mapping. So as each block has 4 words, therefore we will need 2 bits to represent each word. So this block offset will contain 2 bits. Now the set number represents that which set it belongs to. Since here we have only 2 sets which can be easily represented using 1 bit, therefore the set number will have 1 bit. And now since the total number of bits are 6, so the remaining bits will be going to tag bit. And here this tag and set this tag bit and set number together represent the block number from the main memory. Now let's see that how do we know that if it is a case of hit or a miss. So let's make an initial case for our cache memory. So here is our cache memory. Let this be set 0 and this be set 1, and here we have W0, W1, W2, W3, which is of course content of block 0. So as we have discussed that these 3 bits and 1 bit of set number together represent the block number. So to represent this block 0, we will need these bits as the tag bits will be 0, 0, 0. This will be tag bit and this will be set bit. So here we will be representing the tag bits. Now we have here 8th word, 9th word, 10th word and 11th word. So you know that these are stored in second block. To represent the second block, we will use bits 0, 0, 1, 0, where these bits will be tag bits and this bit will be set bit. So here we will be representing the tag bits as we used to in associative mapping. Now let's move to set 1. We have 4th word, 5th word, 6th word and 7th word. From the main memory you can see that this belongs to block number 1. And how do we represent block number 1? We represent it like this. So here this is set bit and these are tag bits. So we will represent the tag bits here and we have set here. So now we have here word 12, word 13, word 14 and word 15. So from this you can say that these belongs to third block, which you can represent as 0, 0, 1, 1. Here these are tag bits and this is set bit. So it can be easily represented here 0, 0, 1. Now let us assume that the CPU looks for physical address 0, 0, 1, 0, 1, 1. So first we will be dividing it in 3 parts. This will be block offset, this bit will be set bit and this will be tag bit. So to search for this in cache memory, we will be first looking at the set number. So here it is 0, therefore it must be lying in set 0. Sorry, we must be looking at set 0. So here we come in set 0. Now after coming in set 0, the CPU will be looking at each tag simultaneously as it used to do in the associative mapping. So first it will be look at this tag. It will look at this tag, that is 000, which doesn't match this tag, and then it will look at this tag, which is 001. It matches this. Then we will look at this block offset to know what was the exact word it was looking for. Since this block offset is 1 1, so it must be looking for, like you know that 0 0 means 0, 0 1 means 1, 1 0 means 2, and sorry, and 1 1 means 3. So it must be looking for the third word of that block. So here the third word is, this is zeroth word, this is first word, this is second word, this is third word. So this was looking for word 11, which was present in cache memory. Now, so this will be a hit. Now let's have another example. Let the CPU is looking for 0 1 0 1 0 0. So first of all, we will be dividing it in three parts: block offset, set number, and tag. So here first we will be looking at the set number and we will be going that set. So here it is 1, so we'll be going in set 1, and now we will be looking at each tag and look for the tag that we have here. So here we have 0 1 0, so we'll have to look for this tag in set 1. Here in set 1 we have tags 0 0 0 0 0 1, and that's it. So we don't have 0 1 0 in set 1 here, so it is not present in cache memory, so it is miss. So I hope that you have understood how the set associative mapping works, and we can have other examples where this can be three-way set associative or four-way set associative. The only change will be that in each set the number of lines will change based on this number. So now let's look at the advantages of set associative mapping. So here are some advantages of set associative mapping. First of all, less conflict miss than direct mapping, because of course it provides us the freedom to choose any cache line inside the set number that we calculate through the formula, and it is simpler than associative mapping because it gives us a formula to choose the set, while in associative mapping we were allowed to place any memory block in any cache line, so which was very complex to calculate, and thus it has a very good performance. So now look at some disadvantage. So, some disadvantages are that, of course, it is more complex than direct mapping, and it is slightly slower. So, I think you must have understood what cache mapping is and what these different types of cache mapping do and how are they performed, namely direct mapping, associative mapping, and set associative mapping. So, for a quick comparison, I can make a table. So, here is a comparison of all three types of cache mapping. Let's make the table. So in this column we will be having the feature here, direct mapping, here associative, and here set associative. So placement of memory block, here it is one fixed line, here any cache line, and here any line in a fixed set. Next we have address fields. So here it was tag plus line plus block offset. Here it was tag plus block offset, and here it was tag plus set plus block offset. Now in hardware complexity, direct was very simple, so complexity was very low. In associative it was very high, and in set associative it is medium, you can say, of course greater than direct. Cost, so cost was very low in direct, it was high in associative, and moderate in set associative, because it was combination of both. Next, conflict miss, it was high in direct, of course it was very low in associative, and it is kind of medium in set associative. And finally, let's come to speed. So direct was of course fast, set associative was slower, and of course as compared to set associative and direct associative was slower, and as compared to associative and direct, set associative was moderate. So we have discussed all three kinds of mapping, and here we come towards the end of this lecture, which was about cache memory, cache mapping, three types of cache mapping, and how they are done. I hope you liked it. Thank you. Have a nice day.